So this is how we use 3x3 determinants for the cross product. Here's our fact. A cross B is the 3x3 determinant with ijk as my first row, the components of A as the second row, and the components of B as the third row. This is actually a formal expression up here. What that means is this isn't really a valid determinant, because determinants are supposed to have rows that are scalars, and up here I have rows that are vectors. But what we understand this to mean is that if we apply the formula for the determinant, the 3x3 determinant, and interpret it, say, this way, we do get a bunch of scalars times a bunch of vectors. So if this first row is a bunch of vectors, it's okay, it still works out, it still makes sense to write this expression. So let's do an example. Let's do 1, 2, 3 cross 1, 0, negative 1. I express that as a 3x3 determinant, ijk, 1, 2, 3, 1, 0, negative 1. And then let's apply this definition of the 3x3 determinant. So it's going to be 2, 3, 0, negative 1 times I minus 1, 3, 1, negative 1 times j plus 1, 2, 1, 0 times k. And then you evaluate these determinants. 2 times negative 1, which is negative 2, minus 3 times 0 is what this determinant is equal to, so it's negative 2. 1 times negative 1 minus 3 times negative 1, so that's negative 1 minus 3, which is negative 4. And 1 times 0 minus 2 times 1, so that's 0 minus 2, so that's negative 2. So I get negative 2i minus negative 4j, so that's plus 4j, and then plus negative 2k, so minus 2k. So question 2 is this. I'd like you to show that A cross A is equal to the 0 vector for any vector A. All right, so just show that from, the definition of the cross product in terms of a 3x3 determinant, or from the original definition, whatever. Anyways, it's not too hard to do. Let's look at some properties of the cross product. First of all, we introduce the cross product to be a vector which is perpendicular to both A and B. And I already asked you to do that for question number 1. I asked you to show that indeed this is true, which is equivalent to showing that A dot A cross B is equal to B dot A cross B, which is equal to 0. And that's the 0 scalar. The second property is that the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times sine of theta. So this looks a lot like the formula for the dot product, which is A dot B is magnitude A, magnitude B, cosine theta. We have sine theta here, but note that this is the magnitude of A cross B and not just A cross B itself. Where does this come from? Well, if you take A cross B and take its magnitude and square it, you can show that it's equal to the magnitude of A squared times the magnitude of B squared minus the absolute value of A dot B squared. And the absolute value of A dot B squared is the magnitude of A squared times the magnitude of B squared times cosine squared. You can factor out 1 minus cosine squared, which is equal to sine squared. Then taking square roots and noting that sine of theta is positive whenever theta is between 0 and pi, which we assume it to be, we can take square roots and we get this. Great. A corollary of this fact is that A cross B is equal to the 0 vector precisely when A is parallel to B. So this is a generalization of question 2. This comes from the fact that the magnitude of A cross B is equal to 0 precisely when sine of theta is 0, which happens when theta is equal to 0 or pi. Finally, the direction of A cross B is determined by the right-hand rule. If I draw A and B so the angle theta between them goes this direction, we're always choosing theta to be between 0 and pi. And so theta is going from A to B. It's important that we're taking it from A to B. Then the right-hand rule says if the direction from A to B is curling our hand around this way, then the A cross B is going to be pointing up the direction of our thumb. So from A to B is here. Right hand rule says A cross B goes up. So this determines A cross B completely. If we have two vectors that are parallel, then the cross product is 0. Otherwise, they're not parallel, which means that they don't lie in the same line, they form a plane, and there is a unique line that's tangent to, perpendicular to that plane. Which vector is the cross product? Well, it's perpendicular to both of them. Its magnitude is given by this formula, and its direction is given by the right-hand rule. So that determines it uniquely. So here's another nice way of looking at the cross product. In fact, looking at the magnitude of the cross product. It turns out the magnitude of the cross product, which is the magnitude of A times the magnitude of B times sine of theta, which is the angle between A and B. It's also equal to the area of the parallelogram with sides given by A and B. So if I have A and B, I draw them with the same initial point. Then I translate A up to here and B up to here. I get a parallelogram. Turns out that the magnitude of the cross product is equal to the area of the parallelogram, because the parallelogram has area equal to the length of one of its bases times the length of a height, which is the length of a perpendicular dropped from one of the bases to a parallel base. And well, how long is this guy? This is a right triangle right here. This hypotenuse has magnitude b, whatever the magnitude of b is. This is theta. This is the opposite side, so this has length magnitude of b times sine of theta. Great. Height is that. The base is a. So AB sine theta is the area, and that's precisely the magnitude of the parallelogram. So question number 3, let's find the area of the triangle with vertices given by these 3 guys. So let's think about that carefully. First, how does the area of a triangle maybe correspond to the area of a parallelogram? Second, how can we use these 3 points to get some vectors that describe some parallelogram, and then get the area of that and translate that all back to a triangle?